Thank you, Ryan. Thank you very much for your welcome. I'm very happy to be here. So today I'm going to talk about nanomaterial for transparent electrodes and talking about the properties, some challenges, and some prospects. So this is a typical picture of Grenoble during the winter. There is the old part of the city that you can see, and there are some mountains around. And the nearest ski station is about 30-35 minutes by car. So it's possible to go there, for example, one morning and to ski and to come back in the afternoon in the lab. That's what people do from time to time. So I'm going to give a short introduction about transparent electrodes. Even probably most of you know that already. And then I'm going to focus a bit my talk about transparent conductive oxides. But main of my talk will be, as Irene said, on metallic nanowire networks. It's an introduction on problem of stability and what we can, our approach with simulation as well. And I would conclude at the end. So I wanted to start working in photovoltaics, and so I went in Australia for sabbatical year in 2006, 2007. And I worked there in Sydney at the Center of Excellence of Photovoltaics. And then I discovered there when we want to make an efficient solar cell that we have to have a transparent electrode. And what I like is this idea. I said, okay, there should be an interesting physics to be done for a physicist because there is a compromise for material to be transparent and to be conductive as well. And I found that was interesting. And actually, transparent electrode can be used in a lot of different applications, as Irene said. And for example, for touchscreen, for transparent heaters, for flexible LCD, OLED, smart windows, solar cells, and other applications which are probably less well known, that radio frequency applications or thermotherapy and so on. There are many different applications. And I found these topics interesting because we can make fundamental physics, but as well apply this as well to a lot of different devices. An example about, for example, smart windows. There are different technologies. And one of them concerns, for example, the electrochromic technology. And so a smart window that changes the phase of a glass from a transparent to either a translucent or opaque state. And to do so, you have to apply a voltage. That means we should have transparent electrodes. And that's a nice picture with two different states from Sage electrochromics, where you have, for example, these windows here in offset, and this was an on state. And that helps quite a lot to either saving energy costs and to increase energy comfort as well. And the physics behind that, you should have transparent electrodes in the blue here, and you have the active layer here, and the ion conductor electrolyte here, and ion storage here. And when it's off, this is transparent, and when it's on, there is a transport of charges, positive and negative charges, and that change quite a lot the transparency of the window. So again, we should have transparent electrodes, and that's the same as well for OLEDs as well, or solar cells. So the main feature for transparent electrodes that concern so a lot of devices, and all transparent electrodes are made from nanomaterials. We are not able to make to deposit a single crystal material which can be transparent and conductive and rather low cost. So they are all nanomaterials. And to have an efficient integration, we should look for specific properties. So we will talk about the physical properties later on, but as well a low cost. And as well it depends, it's very application dependent, but often, for example, we need some, for example, for organic photovoltaic integration, we need some low temperature process, for example. And so there are specific requirements. About the physical properties, we always need to have optical transparency and a good conductivity. So this is a kind of a trade-off between these two properties. And for some cases, for some application, flexibility is interesting. And as well, haziness, for example, could be a key point. Haziness means this is a ratio between the transmitted diffuse scattering divided by total transmitted light. And for sure, it should be stable and environmentally friendly as well. There are different materials for becoming transparent electrodes. For example, the most well-known are transparent conductive oxide, TCO, but as well graphene, carbon nanotubes, metallic grids. And I'm going to talk a bit more later on about metallic nanowire networks, because for me this is a kind of a passion for me at the moment. So one way to show the properties of a transparent electrode is often to put here in y-axis the transparency linear scale and versus electrical sheet resistance for a thin layer, for example, in log scale. And the target is here. We are happy when we have transparency about 90% and a sheet resistance about 10 or 20 ohm per square. This is the target. And we have two kinds of materials. Either we consider oxide or polymers. And that means they are very transparent but not conductive at all. And we are going, for example, to dope them to make either conductive polymers or degenerated semiconductors and to try to shift them towards the target. Another way is to start with metals. They are very conductive, but they are totally opaque if they are thick enough. And the way we can work with a spatial distribution of metallic materials in order, again, to reach the target. That's the case of a metallic grid, for example, or metallic Nanowire network. And this is, again, a compromise between electrical and optical properties. The more material we put on a glass substrate, for example, or a polymeric substrate, the more conductive will be the layer, but it will become less and less transparent. So it's a question of compromise. So the main material family concern transparent conductive oxide. They have been used and have been investigated for, let's say, 4 or 5 decades. And the three big boys concern indium tin oxide, ITO, fluoro-doped tin oxide, FTO, and aluminum doped tin oxide, AZO. The advantages are rather well known and well used. They've been rather well investigated. They could have good or even very good physical properties. So drawbacks, they are oxide, so by nature they are brittle. And for some of them, they could be scarce or rather expensive. That's the case of indium. This is why we would like to stop using ITO. And often we need a vacuum to deposit them, and often as well high temperature. So this is why there have been some emerging TCM, let's say the last 10, 12 years, with graphene, carbon nanotube networks, conductive polymers, metallic Dunaway networks, or grids. Some appear to be rather promising, with good or even very good physical properties. They are still rather new materials. It's rather a new scientific area, and there are still places for innovation and imagination. If you want to be original with TCO, it's still possible, but you have to wake up earlier in the morning. And for example, on conductive polymers or metallic networks, it's still possible to be innovative. Maybe not in 10 or 20 years, but the drawbacks are not well known. They are just starting to be integrated in some devices, but they are not well known compared to the TCOs. They might have some problem with stabilization for some of them. And some could be expensive as well. If you want to have very good graphene deposited at high temperature by MOCVD, it could be expensive. So often to quantify this compromise between optical transparency and electrical resistance, we use figure of merit. So still the most well-known one was proposed by Heck in 1976, a long time ago. And saying this is a transparency to the power 10 divided by sheet resistance. We want to be as transparent as possible, so T should be as high as possible, but the sheet resistance should be as small as possible. And so if you plot the figure of merit versus the amount of materials, you are reaching a maximum. So when we are here, we have put a lot of materials. We are very conductive but not very transparent, and here not very conductive but very transparent, and that's a kind of a compromise. So what I've said before, if you put transparency versus the sheet resistance in ohm per square, you can have some ISO values of the figure of merit, and the target is somewhere here. Okay, so I'm going to talk a bit about transparent conductive oxide briefly, saying that there are thin oxide layer. The thickness is about 200, 300, 400 nanometers thick, and so they look like this. This is the SEM picture. The scale bar is 200 nanometers, so you have a thin polycrystalline layer with a lot of grains. So the grain boundary could play a key role. And for this FTO layer, you can as well see there are some twins within grain as well, which can as well scatter electron. And so we are for sure using, for example, a 4-port points to measure sheet resistance, and as well a spectrophotometer to measure the total transmittance or the haziness, for example. And the point is that if we want to optimize electrical conductivity, sigma, which is inverse of the resistivity, this is directly equal to the carrier density times the mobility times the charge, electron charge. And if we want the sheet resistance to be as low as possible, This is our resistivity divided by thickness. That means if we want the sheet resistance to be as low as possible, we have to increase the carrier density, to increase the mobility, and to increase the thickness of the layer. That's the way to increase the electrical transport. But for the optical transparency, if we want to decrease our absorption, we have to decrease NC and we have to decrease the thickness. This is illustrated by these two curves here. We have total transmittance versus the wavelength. If we increase the carrier density, we are going to increase the plasmonic absorption. That means the window within which transparent electrode is still transparent is going to be narrow and narrow, especially in the near infrared, but you can reach as well a bit the part of the visible as well. And that's the same for the thickness of the layer, the total transparency versus the wavelength. When you increase the thickness, we are starting to be less transparent. So the problem that NC should be high to have a good electrical resistance and low to have good optical properties, the same for the thickness, so it's a kind of a compromise. There's just one parameter in which there is no compromise at the mobility. The higher the mobility, the better will be the transparent electrode. You see why a lot of studies, a lot of investigation are focused on trying to understand, to measure, and to optimize the carrier's mobility. So for sure, there are different electron scattering mechanisms. The probability of being scattered for an electron between the time t and t plus dt is proportional to, is equal to dt divided by τ1 plus dt divided by τ2 and so on. When τ1, τ2 and so on, this is a scattering time associated to different scattering mechanisms. So we have to add the inverse of this characterization time. It means that the inverse of the total scattering time, this is the sum of the inverse of the scattering time for each mechanism. And when you see the conductivity, which is given by this for electrons, for example, this is proportional to tau. That means resistivity is inversely proportional to tau. And that means we have to add the resistivity, and saying that the total resistivity is just the sum of the resistivity associated to the different scattering mechanism. And in case of transparent conductive oxide, we have the bulk contribution. This is the phonons and impurities, for example. This is the grain boundary, could be twins, and as well the lateral surfaces as well. So there are a lot of investigation to understand and to optimize the mobility. And for example, here this is a recent article published in our lab where we plot the mobility of aluminum doped zinc oxide versus the carrier density. And there are some conditions where we are more, the mechanism is more the grain boundary, and if not, it's more the impurity. And in this case, it's more both of them, impurities and grain boundaries as well. Haziness was important as well. So haziness, again, is the ratio between the diffuse transmitted light divided by the total transmitted light. And you can see, for example, a standard FTO as state of the art, a normal one and an hazy one here. And there was an interesting article. There are a few examples in the literature where people, for example, here, they studied dye-center solar cells. And they showed that the efficiency of their own dye-center solar cell versus the haze was linearly increasing, and that's interesting. There are, I would say, a few teams in the world were able to make dye-center solar cells with an efficiency above 10%, and they were able to reach that because they were increasing the haziness. And we found a way in the lab to have a FTO which is hazy like this. Just before depositing the FTO, we deposited some zinc oxide nanoparticles on a glass substrate. And depending on the surface coverage by the zinc oxide nanoparticles, we were able to vary the haziness. This is the transparency versus the wavelength for the bare glass, total transparency and the diffuse transparency. And depending on the surface coverage by the zinc oxide particles before depositing the FTO, we were able to vary the S factor. This is, for example, the total transmittance versus the zinc oxide nanoparticle surface coverage. Total transmittance is decreasing a bit. Sheet resistance is increasing a bit. And we're able to change quite a lot the S factor. And with these techniques, okay, we're losing a bit of transparency, we're increasing a bit of sheet resistance, but still in a reasonable range. But we're able to have very large S factor. So we are scientists, we can't extrapolate things, but if we would allow ourselves to extrapolate, we would, let's say somewhere here, we have an S factor of about 50%. If you look here, 50% would be here, so we would have a very high efficiency for a solar cell. On the paper, it's very simple and easy, it should work, but then we try with 3 different types of solar cells with experts in these solar cells, and the integration problem is not that easy. So we had some problem with delamination, for example. Solar cell works well with commercial FTO, but with our FTO, especially a diffuse one, it's a bit rough, so there could be some additional problems on. So again, on the paper, it's very easy when people know very well how to make a device, saying, hey, we are just going to replace this layer by our layer, and you should have more efficiency. Sometimes it works, but often we can meet some difficulties. Is there any question about TCOs? Yeah.
I just ask, the work you mentioned, I think it was just published this year. I think it was Viet that even did it, where you looked at the mobility in the zinc oxide. I missed, how is the mobility tuned in the zinc oxide?
Oh, yeah, we varied several parameters. In this case, we varied the doping level. We varied as well the thickness of the layer, so that changes the grain size, for example. And so you can tune the impurities or grain boundary scattering. Okay. And as well, we try as well to UV treat as well these layers. So you can play with different parameters, either during the growth or making some post-deposition treatment. And afterwards, we are analyzing and trying to understand which is the main scattering mechanism. Okay, so metallic Dunaway networks. How I discovered that, I went with some colleagues, we went to Liège in Belgium, and we made a stop in Paris, and there was a big event about what else after ITO. And there was a young scientist who was talking about metallic Dunaway networks. And before starting working on photovoltaics, I was working with a bit of physical metallurgy. And I say, okay, I know things about metals. And when I see this topic, I say, wow, for FSC, that should be very interesting to work on that. And then the young scientist, whose name is Jean-Pierre Simonato, he works in Grenoble at the CEA, and so I sent him an email and say, okay, I found this topic very interesting, can we meet? And so we had lunch together, and then it was, something like 8 years ago. And now we have been working quite well together, and that's pretty cool. You see why I love as well this job, that we can meet people. We can travel, we can meet people, and that's pretty cool. I love this as well. That's a very nice aspect of our work. So, I'm a physicist. I don't have a very good relationship with chemistry, but I interact with chemists, and chemists, they know how to make metallic nanowires. They use a polymer which is called PVP for polyvinyl pyrrolidone, and they use some very small silver nanoparticles, which have some crystallographic facets. And this PVP, this polymer PVP, is going to adsorb preferentially on the 100 surfaces here, leaving free the 111 planes here. And this is where the growth is going to occur. There will be more silver atoms here and here, and this is why at the end we have a one-dimensional growth. Schematically, it's something like this. So we have a 5-fold symmetry with some twins. We have long 100 planes, which are covered by PVP, and the 111 faces at both ends, which are free. If we make a TEM picture here, the scale is 50 nanometers. We have very long nanowires. If we make a zoom here, we have silver, the vacuum, and here a thin layer of PVP that says 3-4 nanometers, which have been used to help the one-dimensional growth, preventing the lateral growth to occur. And so we can buy commercially, or we can collaborate with chemists to have diameter, silver nanowire diameter of, let's say, 100 nanometers, and length about a few microns, a few tenths of microns, or even a few hundreds of microns in some cases. And so we receive that in solution, and you can deposit these nanowires on a glass substrate, on a polymeric substrate, using either spin coating or spray coating, for example, or Rollmeyer, for example. And for physics, this is a kind of a density problem. If we put an axis here, this is network density. This is counted as the number of nanowires we put per surface area, or what we prefer is the areal mass density. This is the amount of silver, for example, for silver nanowires. In terms of milligram per square meter, we have put on a substrate per unit area. And below a critical point, there is no percolation. That means between the two electrodes at opposite sides, there is no path for an electron to go from one side to another side. Then suddenly we reach a kind of a critical density, and above this, we have a percolative regime. And that's what we call stick percolation. It has been studied for more than 4 decades by people. And especially this is the percolation theory, saying that n is the density, the number of nanowire per unit area, minus this critical density to the power minus gamma, and this is proportional to the resistivity. That means the resistance is proportional to the resistivity of silver nanowires, which can depend on the diameter, times n minus n to the power minus gamma. And I'll show you later on that experimentally, if we plot, for example, the minimum of the resistance observed during a thermal ramp versus the areal mass density of network, we have this point, and we can fit this point easily with this curve, and it's working pretty well. And here we have the critical network density or critical areal mass density, and then when you're reaching this value from the just above, the resistance is diverging. And there is so this is well known. I mean, the first formula, so NC is equal to something like 5.64 divided by the square of the length of the nanowire. This has been already derived in 1974 by Peak, for example. So it has been studied for more than 4 decades. There's another transition between the percolative regime and above. This is what we call the bulk regime, which is much well known and well understood, but we can see that experimentally. For example, if we plot here in log-log scale the increase of temperature divided by the square of the intensity, thanks to the Joule effect, versus the function of the transparency of the network, you can see there are two lines for the data in the percolative regime and the bulk regime. And the same if you are plotting as well the same function of transparency versus the sheet resistance as well. In log-log scale, you can see as well transition between the percolative and the bulk regime. So this transition is less understood compared to the stick percolation. But it's, yeah, we can still observe that experimentally as well. The two main advantages of silver nanowire networks that the networks are still transparent in the near infrared. We can see that. The transparency versus the wavelength. You have transparency for bare glass. And this is the one from the silver nanowire networks. You can see the silver nanowires. There are some large gaps between silver nanowires, which give rise to the transparency. And even in near infrared, we are still very transparent. If you compare with a TCO, so both sheet resistance were about 10 ohm per square, and transparency in the visible are about the same. But in the near infrared, there is some plasmonic absorption, which means that in near infrared, TCO is a transparent electrode, which is not transparent anymore. So if we have, for example, if we target an application in near infrared, it's better to have silver nanowire instead of a TCO. And as well, it's very flexible. We measure here the electrical resistance after bending cycles with a radius of curvature of 5 millimeters. And for ITO, for example, after only 1, 2, 3 cycles, we have multiplied the resistance by a factor of 20. It's much better with FTO, but it's so flexible for silver nanowires. We can do that for thousands of times. There is no problem. It's very, very flexible. That's the main two assets of silver nanowire networks compared to other materials like TCO, for example. What we did, we observed as well, we measured the resistance versus temperature during thermal ramp, where we increased temperature of 15 degrees per minute. We started with a very high resistance, and then this resistance was decreasing, reaching a minimum, and then kind of a divergence of resistance. So we kind of intuitively guessed that it would be a curve like this, because at the beginning you could have some desorption. This is the SEM picture just after deposition, when we anneal for 10 minutes at 200 degrees, so we can see the organic residue around as dissolved. And then we have a local sintering at the junction between nanowires. There's a nice sintering, because at the beginning when deposit nanowires, often the contact is rather small, so the junction resistance are high. And if we perform an annealing, for example here 10 minutes at 300 degrees, you can see there's a nice local sintering, and that helps to decrease the junction resistance. And then if we perform a 10 minutes annealing at 380 degrees, then we have what we call spheroidization. This is a morphological instability, which is called plateau relay instability. And for sure, the network is, has lost its percolative nature. This is why the electrical resistance is going through the roof. Okay? And this is exactly the same that for water, for example. So we can play with that in our kitchen. At first, you have a cylinder and then some droplets, because the surface energy of droplets or spheres is much lower compared to the surface energy of a cylinder. Okay? So this has been well known and explained by Lord Rayleigh in 1878, something like this, a long time ago. So we guessed that we would have something like this, but well, we didn't guess at all that from time to time we have a kind of discontinuous decrease of the electrical resistance. And for example, either during the increase of temperature, we can observe the discontinuous decrease, or as well, if we are at constant low temperature, let's say 100, 120 degrees, especially for network, which has a low network density, just above the critical density, we observe this kind of discontinuous decrease like this. And with Daniel Langley, who was a PhD student coming from Australia, we did a small model. This is again resistance versus time at a given degree, and we can, given temperature, let's say 120 degrees, and we can see some steps when we wait a bit. And then we thought that, okay, the network can be a schematic way to represent the transport electrode could be like this. We have two electrodes at both sides, and when we are hitting a bit the network, some junctions are becoming more and more efficient in red, for example, and suddenly we can have what we call an efficient percolating pathway. And then if we wait a bit longer, there will be another one, okay? And they are supposed to work in parallel. So that means the inverse of the equivalent resistance after n plateaus like this, it could be the inverse of the initial resistance, which was very high, plus n times n divided by the resistance of an efficient percolating pathway. And if we plot, for example, 1 over the resistance versus the number of plateaus we observe, experimentally it fits rather well. We can have a linear correlation, that's cool. The point is how we can calculate this. We can say we can use what we call the Pouillet's law, saying that the resistance of a cylinder is the resistivity times the length divided by the surface area. But we have to put a K here, because first it's a bit tortuous, and then as well, we have to cross a lot of junction resistance, which are not zero resistance, so K should be larger than 1. And we found something like K, something like 2, 3, something like this. But K is our fitting parameter, because we are supposed to know all of the other parameters. So see what we did, and we published that in Nanoscale in 2014, but we were not able to visualize them, and we had to wait for 2 years more during the PhD of Thomas Saint-Nicolo, who is now a postdoc at MIT. And thanks to specific infrared thermography techniques, we were able to observe this. So there are 2 electrodes here. When we apply 4 volts, for example, and the length should be, between my 2 fingers, should be something like 6 or 7 millimeters. We can clearly see there are some efficient percolating pathway, because thanks to the Joule heating effect. And if we apply 5 volts, for example, there are more and more of this percolating pathway. So that was a rather non-expected observation, for sure. And the point is that we studied as well the effect of the morphology of the sizes of the nanowires. For example, that's an example of the diameter influence on the properties. Again, this is the log of the resistance versus temperature during thermal treatment, thermal ramp. And exactly what I've shown before on denser networks, so we don't see that much discontinuous decrease here. But with different average diameter of 25, 60, and 117 nanometers. These nanowires have been purchased by at Seashell Technology in California. And so they were having the same method to prepare them with different nano diameter. And we can see that for the lower diameter, the solidization temperature is lower, and as well the minimum temperature, minimum resistance temperature is lower as well. So if we plot this temperature versus the 7 nanowire diameter, the red one corresponds to when there is a spherization, and the blue one when we are optimizing, minimizing the resistance. This is the symbols, and the barriers correspond to the fact that we have studied a lot of network with different density, for example, and so we got different results. And if we just use this formula, which comes from the Gibbs-Thompson equation, which is well known in physics cluster, for example, saying that they use that often for cluster for plotting the melting point, and saying it's 1 minus different thermodynamic values, and you have here the radius of the cluster, or here the radius of the nanowire. And it fits pretty well. We have only one fitting parameter, which is this temperature here. So this is the importance of 7 nanowire diameter. So when the nanowires have a diameter which is smaller, we have more and more problem with stability. It's nicer for the H factor, but as well we are going to be more and more unstable quickly. That means at lower temperature and at a lower current density as well. now we can as well see the influence of the lens. For example, we can say the resistance is proportional to the resistivity of 7 nanowires and n minus nc to the power minus gamma. I already talked about nc, which is given by 5.64 divided by the square, length of the square. And so the point that if we are, for example, plotting the 7 nanowire density, n, number of nanowires per unit area versus the nanowire length, this formula is given by this dashed line, blue dashed line here. Okay? And for example, for one given nanowire or length of 7 nanowires, we fabricated different networks with different density. When it's a cross here, that means the network was not percolating. We were not able to measure any finite electrical resistance. And in red, we were able to measure some resistance. And the diameter of this disk is directly proportional to the log of the resistance of the network we measured. Okay? So here we are supposed, it's a kind of a phase diagram. Here we are supposed to have no percolation, and here we are supposed to have percolation. So we can see that roughly it's in good agreement with experiments, but we have spent some time as well trying to understand why there is a difference here, and what is the difference between perfect worlds, I mean straight nanowires with just one length, for example, and with a totally random distribution compared to real world, where we have a length distribution, we have curvature of nanowires, and as well we have kind of a distribution of anisotropy as well. So we have worked on that and published that lately with Dan Langley, still a PhD student who have finished his PhD already 3 years ago, but we are still collaborating a bit. He's in Melbourne, and yeah. And here as well, there is an influence of the diameters. There was a nice paper by Bid and Al in Physical Review 12 years ago, and they showed that the experimentally and theoretically that the electrical resistance of 7 nanowires, that the one from the bulk times 1 plus the mean free path of electrons, which is about 50 nanometers in bulk silver, divided by 2 times the diameter. And they observe, so that means that they observe that when the diameter is lower and lower, the electrical resistance of 7 nanowires is increasing. Okay? And quite a lot, it could be a factor of 2, something like this, especially for small diameter. So we know that from this. We know this because we know the length, we know the diameter, we know the mean free path. We know nearly everything, so we can put everything together. And for example, calculating the electrical resistance versus the RMS density of a network, the diameter and the length, average diameter, average length. This is equal to the instrumental series resistance plus C. So C, I'm not able to calculate it. It depends on the specimen size, for example, and there might be some other parameters. I'm not able to calculate it, so it will be the only fitting parameter, because this one we can measure it. If we deposit a thick silver layer, for example, we can say that the resistance is so small that we are going only to measure experimentally the instrumental series resistance. So we know this. C, we don't know that the fitting parameter with that silver bulk resistivity. We know the mean free path of electrons in the silver. We know the diameter. AMD that we are going to measure minus this, and we know everything here. So we can use to feed the symbols, the experimental data. This is the minimum resistance we observed during a thermal ramp in log scale versus the RMS density in log scale. And the different points correspond to different nanowires, 117 nanometers in diameter, 130 nanometers in diameter, for 2 sets of nanowires as well coming from C-shell technology. And you can see that the fitting is pretty good, knowing that we have only one fitting parameter. And again, this is a very simple model. That's the simplest model we can imagine. So we are rather happy about that. And we can use this equation to have the minimum resistance, but as well, for sure, we can use another equation for measuring the optical transparency. And so that means we have a kind of a formula for the figure of merit. You see what we do here? We use again the ax figure of merit, T to the power 10 divided by the sheet resistance. And we plot experimentally the optical transmittance versus the RMS density. This is a linear decrease. It's rather easy to understand if you are considering the shadowing effect. The more metal you put, the less transparent will be the transparent electrode. The sheet resistance, I already talked about that. We plot it here in a log scale, okay? Still versus RMS density. And if you plot the figure of merit, it's something like this. So we are again an optimum like this. So it's not far from 100 milligrams per square meters. So if you put 1 kilo of silver on the table, the chemists are able to give you 500 grams of silver nanowires. And if we don't waste some it will not be 100% efficient, but if we are using these 500 grams to deposit some silver nano networks with a narrow density of of, let's say, 100 milligram per square meter. With 1 gram, we can make 10 square meters. So with 500 grams, we can make something like 5,000 square meters coming from 1 kilo of silver. So it's not, I know it's not 100% efficient, but that means it's, the cost should be rather low, okay? Even if silver is an expensive material. But yeah, chemists who are making some progresses at the moment for synthesizing to make synthesis of copper nanowires. And all we do here as phases, we can do that as well with other metals. We would be happy to work with copper if copper would be more reducible to fabricate them, and if they would be more stable, because they have big problem with the oxidation of copper as well. So we are happy to have a maximum figure of merit, but as well, it's not only the two parameters are not only optical transparency and sheet resistance. There are some other parameters I've said before. And for example, the AS factor is directly proportional to the mass density. Exponentially, see what we can observe here. And that means for some application, like for a display application, you want to have a very low S factor, often lower than 3%. But if you want to work with solar cell, for example, you're happy to have a large S factor. So it's not only this theoretical figure of merit, but it's application dependent. And for example, if you want to work as display, for example, here, for transparent heaters, it's better to work here at low S factor. But if you want to work with solar cells, it's better to work with a larger area density, because you want to have a larger S factor. So it's very typically application dependent. Transparent heaters is very interesting as well. That helps a lot of things. That helps our airplanes as well to fly at 10,000 meters of altitude, because you can see here there's different colors. So they put here a thin layer of AFTO. And so that transparent and conductive material, when the current density is crossing this transparent electrode, there is a heating thanks to the Joule effect. And this is a way to make defrosting and defogging. And for sure, transparent temperature versus time, when we apply 3 volts or 5 volts or 7 volts, there's a decrease of temperature. Okay, the first paper was coming from the Jean-Pierre Simonato's team in Grenoble about 6 years ago. And that's pretty cool. And so for sure, we did some work on it as well. And if you plot resistance versus time, when we apply, for example, a voltage of 1, 3, 5 volts, and we go down 3, 1 volt, so we do something symmetric versus time, and we measure the resistance. For sure, when we apply voltage, there is a current, so that means the transponder is going to be heated, and so that means you will have more phonons, and so the resistivity of the metals is increasing with temperature, okay? And so there's an increase of temperature when we apply 1 volt or 3 volts or 5 volts, but it's supposed to be constant, and then it's not constant anymore. And the higher the voltage, the more unstable it becomes. When we have stopping, we're putting 3, 1 volt, you know here, we are the resistance much higher compared to this one. So we have some problem with stability. It's not stable. And so if it's not stable, we are not able to integrate this transparent electrode in any device. So we have to work on that. And we wanted to understand where does this instability is coming from. And from time to time, when we make, for example, a voltage ramp, we increase the voltage versus time linearly with a rate of 0.5 volt per minute. And we measure in situ the resistance. And first, the resistance is slightly increasing because of the Joule effect. And then there's a decrease of optical resistance. This is electrical sintering. And then the resistance is increasing, and then it's diverging. And we wanted to understand that. And we observed this with an infrared camera. And we observed as well that there is a crack propagating. It's very analogous to the mechanical cracking. There's a crack occurrence somewhere here. And since we apply a different voltage between the vertical electrodes, there is a current density here. And here you have a concentration of current density. That means it's hotter here. And see why the crack is going to propagate. And we can observe that easily with infrared camera. And within the cracks, we can see that afterwards with the SEM analysis. That is the nanowires were very happy at the beginning. Now they are starting to have undergone morphological instability. It can be seen here. This is a nanowire found from the crack, and within the crack, you can see the crack is very small. It's very narrow. It's a few microns width, but the rest of the samples, it's fine. Okay, so we are not able to measure any more some finite resistance with the 2 points probe, but with the 4 points, you can find finite resistance nearly everywhere, except within the crack. And yeah, and we wanted then to increase the stability. And so we, David Munoz Rojas, who has been working in the lab for the last 3 or 4 years now, he has worked with Judith, someone you know at least a bit, or some of you quite well. And they work about spatial atomic layer deposition. And this is a nice small review they published 4 years ago. And now I think that the spatial atmospheric atomic layer deposition is becoming more and more familiar, because the point is that it's a rather cheap technique and you can go very fast. You can work in atmospheric pressure, and it's compatible with wall-to-wall technology. And it's very complementary compared to atomic layer deposition. It's much faster, but you cannot replace ALD by spatial atomic layer deposition as well, because the precursors should have some other properties as well. So it was a complementary, but that's interesting techniques. And I think David built the first SLD setup in France, but I'm pretty sure that in a few years there will be many in different labs as well. But there's something kind of a growing, interesting field around this atomic pressure, spatial atomic layer deposition. So what we did, we deposited conformally some, let's say, zinc oxide or alumina, for example, around 7 nanowires. This is bare nanowires. This is coated nanowires, observed with SEM or with TM. So again, it's the same TM picture than before. And when we coat them, we can coat them with a thickness, with a conformal layer of zinc oxide, with a thickness of few tenths of nanometers. And you can see that's a nice SEM picture. We can see the 5-fold symmetry, and in blue here, this is for sure a false color, and we can see the zinc oxide coating. And again, if we plot the resistance versus the voltage during a voltage ramp, for bare nanowires, the failure voltage is somewhere at 8 volts, something like this. But if we put 15, 20, 25, or 30 nanometers of zinc oxide coating, the failure voltage is increasing quite well. And if we plot the failure voltage versus the zinc oxide thickness, coating thickness, here we are, this is the blue points correspond to the experimental observation, and we have derived a very simple physical model which comes from a atomic diffusion, silver atomic diffusion models. We have this fitting curve here, which fits well with the experiments, experimental data. Here we are in the safe side, and here we are on the failure side. Okay, so we have published that this year in ACS supplementary interfaces, but as well we work with Jean-Pierre Simonato's team on copper nanowires, and for sure we can get about the same result as well. So that's a nice way to coat the silver nanowires and to make them much more stable then. And now if we do the same than before, measuring the resistance, electrical resistance versus the time, for bare nanowires, that's in black, so we can clearly observe some non-stability, and in yellow with the zinc oxide coating, we can see that it's much more reversible. So we went on working on this, and I think there's an interesting field of research concerning silver nanowire networks. This is why that we can perform some nanocomposite with an oxide as well. For example, see the total transmittance versus the realm density. For bare nanowires and zinc oxide, and we can see that, yeah, when we are putting more nanowires, for sure, we are less transparent, and we are putting zinc oxide, there is a decrease of transparency. And you can see the SEM picture here for the bare nanowires and for the nanocomposite. But the point as well is these optical properties. Optical properties is something like this. The sheet resistance in log scale versus realm density. For bare nanowires, that's in green. We can clearly see there, as before, that there is a critical realm density somewhere here. And here, this is a nanocomposite when we put the zinc oxide layer and the silver nanowires. And we can fit that easily with some simple models. This is only the percolation theory I was talking about before. And this one, that's a kind of a new model, which is, we call that the percolation cluster models. And so it's interesting to see that even below the critical mass density, it's possible to help the conductivity of the zinc oxide layer by integrating some zinc oxide, some silver nanowires, even below the critical threshold. That's something which is rather interesting as well. The point is that we have seen before that the transparency is lower, so maybe there is another point interesting that at the top of the zinc oxide, again, still by using spatial atomic layer deposition, we can deposit some alumina layer, and we can see a TM picture. We have the silver nanowires in black, zinc oxide and alumina here. So this one a bit thick because we wanted to observe that with a TM or with a SEM, but it could be thinner. And again, with a cross-section with the SEM, you have the silver nanowires here with a 5-fold symmetry. This is the zinc oxide and alumina around. Okay? And that's interesting because alumina could be used as a partial anti-reflective coating. This is transparency versus the wavelength, bare substrate. If you put only silver nanowires, if you put silver nanowires with zinc oxide, we are lower transparency, especially when interested in between 400 and 800 nanometers for a lot of display and visible. And if we put, again, 50 nanometers of alumina, the optical transparency can increase quite well. So this is a kind of a partial anti-reflective coating. And the question we can wonder is that we are putting some oxide, but we said before we wanted to work on emerging transparent electrodes because we wanted them to be flexible. Now we are putting, so we work on silver nanowires, but now we are putting some oxide. It's still flexible. The answer is yes. This is minus initial resistance divided by the initial resistance. This is number of bending cycles. We reduced to 5 millimeters. We divided this data by 200 to be able to put the data of ITO. So this point should be normally 200 times above, so nearly in the sky. So for ITO, that's a catastrophe. For bare nanowires, we are here, okay? And this is silver nanowires with zinc oxide. And silver nanowires with alumina, we are even below the silver nanowires alone, okay? So we can find ways to put oxide to protect, to enhance the thermal or electrical stability of silver nanowires and making them still rather well flexible. Why is this one is lower than that? It's probably because we are enhancing the adhesion as well of the layer. Okay, you have some silver nanowires, and then you put an oxide, and if the oxide has a kind of envelope, and if the oxide is happy to adhere to the substrate, that can help as well to have less delamination where we are bending them as well. So as a physicist, we love making experiments, even if I don't make experiments myself anymore. Yeah, I don't have time anymore, that's a pity, but the young guys do that. But as well, we love making simulation as well. So I'm not going to talk a lot about that, but saying just what we can do with simulation. For example, we love to use a Monte Carlo simulation. It's not very new. Already, I saw before that peak, for example, in 1974, they already used a bit this. So what we do, we have two electrodes here, and we are throwing numerically some silver nanowires. And when they are forming a cluster, we put them in blue, okay? And we're waiting to have a percolative cluster through the whole network. And then we stop, and we say, okay, now we are going to count the number of nanowires which were sufficient to have percolation between these two opposite electrodes. Okay, we could be lucky or not, so we have to make that again and again and again. So often we multiply that for, let's say, I don't know, something like 10,000 or 100,000 simulation. And then, for example, we can plot here the probability when we have the percolation occurrence, probability versus number of wires. How many wires we have to put in order to reach percolation. And this is kind of curved like this, okay? That's a kind of a Gaussian. And if we plot in violet the cumulative probability, so here we didn't put a lot of nanowires, probability of having percolation is 0. Here we put enough percolation, enough nanowires of percolation is nearly sure, so we have probability of 1. And one way to define the critical density, saying, okay, when the probability is 50%, okay, we can have the number of nanowires, saying this is a critical number, and we just divide by the surface of the network, and this is the critical density. And we can for sure change the length, and we can observe this formula. Okay, this is well known. It has been done for several times in literature, so there's no new about that. And for sure, if you put the log of NC versus the length, we have something like this. So this is non-percolative region and percolative region. Okay. But in this paper, what we didn't do that only because it was already well known. But we observe, we try to quantify the imperfection in real world, and trying to assess what is the influence on the physical properties of this network. And this is what I've shown already before, so I'm going to talk about that before. I should just make a remark saying that each point you have to make one network and to measure the Riemann density, to make a self-modeling, to measure the minimum resistance, to repeat it again, okay? And so that's a lot of experimental work, okay? So I should, PhD student has to work a lot to do that. What we do as well, often in conferences, people are asking, okay, you are dealing with random network, but maybe it would be better to align the nanowire, maybe in X and in Y. parallel and perpendicular to the electrode. That could help. So we made some simulation with that. This is a critical density versus the percentage of vertically aligned sticks. What we show here, this is a random network here, okay, with a 5.64 here in dashed line. And if you consider trying to align, so it's not very good. But here, as well here, that's a zoom here, we're still above this line, okay? So for us, it's not that very interesting to make them perfectly aligned, because in the Monte Carlo simulation, we suppose the diameter is 0, than only stick. But if we allow to have angular distribution of 5 degrees, it's slightly better. But we are still above the critical density for a random network. For us, that means that random network is cool, okay? Maybe better than to have some align in along X and Y axis. What we wanted to do as well is to look at mixture between sticks and circles, okay? And that, for example, NC for versus the percentage of circular shapes. For example, here we have only sticks, and here we have circle like this, and we put a mixture with this percentage. This is a critical density here. And what's interesting as well is the total length of material divided by the unit area, okay? And we have something like this. We can play with that, and we have as well performed some macroscopic experiments with long sticks and long circles, and the experimental points, they are rather well in a good agreement with the simulation. We are happy with that because, you know, when you are making simulation, if you don't compare with experiments, we can, even if you try to be very careful and honest, we can from time to time make some mistakes, and it's nice to retrieve the same result with an experimental approach as well. And that's interesting because chemists, they are starting to try to make some branched nanowire, for example, and often they ask us, okay, is it more interesting to have branched nanowires instead of only aligned nanowires? And see why we're trying to make this work to answer these kind of questions. Okay, I'm going to go for conclusive remarks. So if we compare briefly the different transparent electrode types, looking at the advantages, drawbacks, and one reference per each. So transparent conductive oxide, conductive polymers, metallic nanowire networks, and carbon nanotube graphene. That's we can talk about that for a long time, as well as application dependent and so on. But I just wanted to make a short table about that. Advantages for TCO, they're already well integrated in some industrial devices, and we have with a good knowledge of them. They could have good or even very good physical properties. But as I said before, there might be some indium scarcity, non-flexibility, and possible high cost for some of them. Conductive polymers, have been rather impressed by the progresses that chemists have done lately, the last few years. Now they are starting to make some conductive polymers with electrical resistance, electrical conductivity, as good as our FTO, which is the state of the art. And that's very impressive. I have a slide on that. I can't go in details because this is full chemistry, but based on P dot, but not only PSS. They try to replace the PSS by other molecules, and now they are starting to have very good electrical conductivity with a resistivity for 2 or 3 10 to the minus 4 ohm per centimeter. So that's very cool. So they could have very good electrical conductivity, rather low cost. The drawbacks is for sure you can't go at high temperature, and some of them, they are not very happy when they are emitting some oxygen or some water. And as well, UV could be not very nice if you want to enjoy that in the solar cell, for example, maybe UV could be a problem as well. So metallic nanowire networks have some rather good physical properties or even very good physical properties. It could be compatible with low temperature solution process fabrication, so it was a low cost as well. Compatible with roll-to-roll and so on. There might be some problem with stability, so we have to be careful with that. For some applications, there would be a too large S factor. That might be a problem for display application, for example, for smart grid, for smart Windows integration, for example. And carbon nanotubes or graphene, they are flexible. They can be fabricated as well by solution processes, which is cool, so compatible often to roll-to-roll technology. Often, they are not that transparent enough for some applications, and there might be some mass production and reproducibility as well. I could have mentioned here as well that there are from time to time some problem of reproducibility to fabricate them as well. For me, there's still a lot of work to be done on transparent conductive materials. I've given some example, P-type TCO, for example. The community knows well how to make N-type TCO, like ITO, FTO, AZO, but P-type is not that easy. And it would be cool because then we could make a transparent PN junction. That would be the window open to transparent electronics for sure. But there are still a lot of problems to fabricate some efficient P-type TCOs. Better control of some properties like the work function, laziness, flexibility. Process at lower temperature could be important for organic photovoltaics, for example. And as well, the nature and property of interfaces is a key problem as well. When you want to make integration, interfaces is going to be very, very important. There are serious alternatives to TCO, like cognitive polymers or metallic tandem networks. Okay? Stability is an important point. When I say stability, I'm talking about chemical, thermal, edging, and electrical stability, all of them. And yeah, we have been able to show that the spatial atomic layer position appear to be rather promising to help the network stability and as well to help fabricating some nanocomposites. And I'm still convinced that a lot of innovation are facing us, for example, architecture, multi-layers, hybrids, and nanocomposites. For sure, various applications are concerned. For example, at the moment, I'm involved in different projects, one about energy harvesting, another one about organic photovoltaics, another one about cold emission of electrons. Could be interesting for X-ray imaging, for making some smaller X-ray emitters, for example. And again, not only one transparent conductive material will win. The choice is very dependent on applications. And that's a general remark. You can do that for all material science as well. A very common example is that bikes, for example, if you remember Pierre and Marie Curie or Albert Einstein riding a bike already more than 100 years ago. And if you look on the streets at the moment, you have bikes made with steel, with aluminum, with carbon. It depends what you want to do, the weight of the bike, the cost, and so on. So again, there will not be just one transparent technology winning later on. It depends so many applications they are placed for a lot of people. I've just put this nice picture from Stapleton and Al. They are coming from Adelaide in Australia, and they've shown some nice nanocomposite with single all carbon nanotubes and silver nanowires. I'm pretty convinced that nanocomposite made with different types of transparent electrode technology, as with polymer, with graphene, with nanotubes, with silver nanowires, with oxide. I think there is an interesting field which is going to be which has opened already a few years ago. I would like to thank my main collaborators. The 6 first were PhD students, or they are still PhD students, and my colleagues. This is David, this is Jean-Pierre Simonato, and Duy who is professor in Liège University in Belgium. We have published a certain number of papers lately, and this is Grenoble, with a picture from the top of a mountain close to Grenoble. So you can see there's one mountain here, another one here, and the third one here. So this is a kind of a Y. There's a Y valley. And we often say that there's a Y valley. There are 3 branches, and one is education, the other one is research, and the other one in industry. Because you have large instruments with neutron reactor, L'Orangerie Institute, or the European Synchronization Facility. And as well, there's a CS. There are as many physicists in Grenoble than in Paris. Knowing that here Grenoble is small, there are, let's say, 500,000 of inhabitants. But I think that 20% of each inhabitant from Grenoble are linked directly with research. Okay? So that's, there's a lot of research in Grenoble. This is Mont Blanc here. This is the top, the highest point in Europe. And yeah, and this is for sure where Joseph Fourier was born and lived there as well, in the 19th century. And so if someone likes physics and likes the mountains, that's a cool place to live and to work as well. Thank you for your attention. It was maybe a bit long. Other questions?
Yeah, I had a couple of questions actually. I noticed that your annealing temperatures for the silver nanowires are much higher than I get. How did you anneal your silver nanowires?
Well, I think the way to answer the question is whether it was in air or in vacuum, probably. We mostly do some air thermal annealing. So I've shown something, and the way to show them, maybe it's a bit too simple, but the point is that the PVP behavior is very tricky. Okay? And one of the first experiments we wanted to do when we started to work in this field, saying, okay, we have an environmental scanning electron-microscopy. Okay? We are going, because I'm in love with plateau relay and stability. Okay? we said, okay, we are going to use a thermal stage under the SEM. We are going to increase temperature. We are going to see how the silver nanowires undergo the morphological instability. Okay, but we went up to 300, 400, 500, 600 degrees Celsius, and they were still intact. Why? Because the PVP around that, even if it's very thin, it needs oxygen to start degrading. But we were making experiments under vacuum. Okay, so they were very stable. Okay, and you see why? If you perform a thermal annealing in air or in vacuum, that changes things because of the PVP, which can degrade with oxygen, but not in the vacuum. Okay, so we performed a bit of thermal annealing in vacuum, but we didn't go very far because we should have done a lot of experiments, and the PVP is very tricky. Okay, I shown some results of the PhD of Thomas and Nicolo. So he was working with Jean-Pierre Simoneau and myself were two supervisors, so between a chemist and a physicist. And one of the goals of this PhD at the beginning was saying, okay, we are going to focus on the role of the PVP. Even after 3 years of PhD, we still don't know exactly the role of the PVP, what is becoming afterwards. Okay, it's tricky. We have tried to make several experiments, and that's surface chemistry, so I don't feel very competent in this field as well. And for me, it's still kind of a mystery. Okay. Have I answered your question?
Yeah, you did. Sorry,
Okay.
I just had a second quick question too. Was surface roughness is a problem with
Yeah.
Metallic nanowires, and I was just wondering if you looked into using SLD, zinc oxide, and the aluminum oxide. Has that done anything to the surface roughness? Has it, or no? It's still just as
No, because we can't ask everything to the SLD as well. It is a so conformal coating, which is a good point, but then it doesn't reduce the roughness. Okay, so maybe one way. So it depends on the application as well. If you want to use just a transparent heaters, not for a display, you don't care that much about roughness. But for example, to integrate that in this transported in organic photovoltaics, for example, that's starting to be very important. So what people do normally is they don't use chemical technique to deposit. More, for example, they use spin coating, and you can put, for example, a conductive polymers, and that's a way to decrease the roughness. But no, special atomic layer position, this is a very conformal coating, and so it can't decrease the roughness.
okay. Thank you.
You're welcome.
So I'm an electrochemist who studies catalysis, and so
Yeah.
I have a lot of electrolyte and solvent around all the time. How do
Yeah.
these wires hold up when you have, so traditionally we avoid meshes
Yeah.
because you get deposits of corrosion at
Yeah.
contact points and you
Yeah.
kill your conductivity.
Yeah.
Is that an issue in here, or is that something that you're looking at in projects? Charge transfer into a solvent?
Yeah, good question. We don't have a lot of experience on that. What we try to look at, we wanted as well to coat some silver nanowires with oxide, and we try to use electrochemistry, for example. We say, okay, I mean, it's well known that zinc oxide or aluminum of zinc oxide, you can deposit that with electrochemistry. So we wanted to do that. But it was not nice, because if you have silver nanowires, we have some, so, kind of cluster here and here, and it didn't help for the stability, and you can diffuse a lot, and you can absorb a lot, so it was not interesting. But
Spatial ALD layers might be interesting, right? Because you can usually put down
Yeah.
a thin insulating layer and still
yeah,
do effective electrochemistry.
Yeah.
Those might hold together quite well. So I use FTO and ITO quite
Yeah.
extensively. And
Yeah.
I know we use them because they're stable.
yeah.
But I'm curious, like, we've avoided any
Yeah.
wires and metallic things for stability.
Yeah. But I think the point is that while silver nanowire, especially for small, short diameter, was not that stable thermally or electrically, it's because of the atomic diffusion, it can be very efficient.
Yeah.
But that's the same as well, because you are having some edge effect as well. And this is why we're using that as well for making some low temperature electron emission as well, because of the low dimension. And so that's cool for a lot of things. But as well, that's a problem, as you said, because of the, for example, electrical, because we are going to have to concentrate a lot of electrical field locally, and this is where some problems are going to occur. So again, SLD could be helpful as well, because we can deposit zinc oxide as well at aluminum doped zinc oxide. Not as good as a state-of-the-art AZO. Our one with SLD is not yet very conductive. And FTO. The FTO we're depositing is at too high temperature, let's say 420 degrees. So maybe we have to coat first with zinc oxide alumina with SLD, and afterwards to use a spray pyrolysis to deposit some FTO, which is very good conductor. But we have to be careful with that as well. You have, again, like for SLD, you have drawbacks and advantages of silver nanowires, and the small diameter make it very interesting, but as well was fragile in terms of stability and for other things, and electrochemistry as well, yeah.
Just getting back to this annealing and vacuum or air, I mean, wouldn't annealing and vacuum work better?
No, I mean,
no oxygen there, and heating things up in the presence of oxygen, you think would increase kinetics and so on. So I'm actually surprised to hear that you rarely anneal and vacuum.
well, again, if we have choice, we are trying to use some low-cost technology. And if I say, yeah, it's compatible with roll-to-roll, silver nanowire, transport electrodes are compatible with roll-to-roll, but then afterwards, if you have to make annealing in vacuum, so somewhere you have to cut them and to put them in a vacuum, so you can't do that with roll-to-roll. That's the first, economical reason, not scientific reason. The other point is that, yeah, we choose from the beginning to make some air annealing, knowing that it was very different compared to the vacuum. So we don't want to repeat all we have done on air to do that in vacuum again. And I think it was maybe less reproducible as well. Less reproducible. And yeah, but it's mainly as well, so the PVP is less degrading, and I think as well to decrease the junction resistance was a bit less powerful as well. Okay? But I don't say it's not interesting. I just said that we are doing the same job. Sometimes you have to choose some path, and we chose the air annealing because we saw it's working well, and so it's less expensive and so on. And we made a bit of experiments with vacuum, knowing it was different, but yeah, we didn't go very far in this.
Yeah, I agree it's more practical, but
yeah.
in papers, people are trying to get the best results, so they don't necessarily care about
Yeah,
cost.
yeah.
It's hard to compete.
Yeah. No, you're right.
To get rid of your PVP, right?
Yeah.
Under vacuum, that probably doesn't go.
No, it doesn't go, yeah. Sometimes, even at 600 degrees, silver nanowire is still stable, but sometimes there's a leak, and so silver is going outside. So with a TM, for example, we can see that there is a shallow cylinder with just a PVP, and then you have a bigger particle with silver here, because again, the silver just wants to minimize the energy of the system. And if you have big stuff like this, it's much better in terms of surface energy compared if they would fill the whole hollow tube. And for us, that's a big problem as well, because we don't want to see that. We don't want to see a big metallic particles. We are going to make some short circuit. It's going to be, very opaque and not helping the conductivity. So we didn't have good feeling with vacuum annealing. I'm not saying it's not interesting, but we didn't make a lot of experiment on this. Another question? No? So thank you.
Thank you.